Okay, so it is my pleasure to introduce Ellyne Kinney, who is the Principal Solutions Engineer at MDA. I had the pleasure of first meeting Ellyne when we at the Outer Space Institute became reached out to MDA to engage them on a number of different issues. And I'm so glad that they then put us in touch with Ellyne. It's always wonderful to talk with her and get her perspectives, extremely knowledgeable, and has a great range of expertise. So as those who are listening, many of our trainees, if you're looking at the different types of paths that you could go within planetary science, exoplanetary science, definitely take a look here at what Ellyne's been able to accomplish. So she's worked at Space Telescope. She's been a contractor at Goddard. She's worked at the National Optical Observatory. Is that the right one? Or
the National Solar Observatory.
National Solar Observatory. Sorry, the National Solar Observatory with Google. Okay. Yeah, and she's had and so forth. So she's had many different experiences in different contexts, both as an astronomer, as an engineer, merging those together. She's had awards from Space Telescope, Goddard, and Google. And I could just go on, but instead I should take a step back and let Ellyne do the talking from here. So Ellyne, thank you so much for joining us.
Thank you for inviting me. I'm very happy to be here today. Today I'm going to be talking about my experience or some issues that I learned and became aware of while I was working at Google. Google for a short period of time owned Terabella. And Terabella is a new space startup that built and launched the Skybox satellites. And so I had a very interesting experience of coming from this background of very heavy in NASA, traditional NASA space projects, and saw how Silicon Valley approaches building, operating, and launching space satellites. And so I wanted to talk a little bit about what I learned there and how that is creating a new problem for us, which is a huge increase in the amount of space debris we're seeing, particularly in low Earth orbit. So maybe we should go ahead and start the presentation. Am I the one who should hit the share button or not?
Please go ahead.
Okay. So, so my title today is Satellites and Sustainability. And I'm going to start this talk at an unlikely place, which is with the traditional telephone. And so I would assert that the story of space debris starts here, and it's with the telephone. Starting in the early 20th century, governments and industry made large investments in R&D and development labs. And companies such as Bell Labs, General Dynamics, DuPont, Bayer, the US Army and Navy research laboratories established companies to develop many of the new inventions that are now part of everyday life. In Canada, World War II spurred rapid growth in the manufacturing sector, and R&D laboratories to support Canadian industry grew as rapidly to support industry. The Defense Research Board and the Canadian Armed Forces led the development of systematic planned R&D activities. How many folks here actually remember having a telephone like this one in their homes? And it depends a little bit. Maybe you didn't. Maybe you grew up with something that looked a little bit more like this, which is your typical cell phone. But if you pick up a 1950s era telephone, one of the first things you notice is that the build quality of these units was amazing. The phones of that era were meant to last decades, and they are heavy and they feel really well built. A customer could only buy a telephone from the phone company, and they were quite expensive. It was unusual for families to have more than one telephone in the home. They were hardwired into the phone network and they stayed in one place in the home. And if you wanted a second line, you had to you had to have a contract with the phone company to install it, and it was quite costly. And most homes did not bother with the expense of a second telephone line. So if we go back to these wonderful little devices here, our cell phones, you know, one of the things that I often contemplate is this really isn't a telephone. This is a computer in your pocket. When we think of these phones, they really are like very powerful computers. And while the traditional telephones really only did one or two things, you could make a telephone call, you could call the operator to find out the time or the weather, but that was pretty much it. It was just for making calls. The new phones that we carry, they're a camera, they're a clock, they're an address book, an atlas, a compass, music player, book reader, news channel, bank interfaces, and hundreds of other applications. Oh, and yeah, you can still make telephone calls with them too. And so over the last 60 years, the telephone has undergone a huge transformation. In the 1950s and 60s, it was heavy, expensive, stationary, and single purpose. But in the early 70s, the first mobile phones were invented, and these were also quite heavy, expensive. They often came in big leather bags that you carried around. And they were still single-purpose devices. But then in the late 1990s and 2000s, we started to see the smartphones. And they were still quite expensive, but they were really much more capable. And with a small but growing number of applications that customers could install themselves. And nowadays, many people wander around with these small, powerful multi-purpose computers in their pockets. And some of the impacts of that are really great, and some of them we are learning are less great, you know, in terms of taking your time and attention away from things that are perhaps more meaningful. But with all new technology, there is a period of figuring out how to use them wisely. And so what drove the changes in phone technology so dramatically? What does the mobile phone have to do with the space industry? And if I care about space debris, why do I need to understand the evolution of the telephone and mobile computing market? And so it turns out that the evolution of the space industry and the consumer electronics industries are interlinked. Cold War and Apollo-era R&D efforts by the government and academia stimulated the creation of new inventions by proposing, funding, and organizing R&D efforts in the area of space exploration, rocketry, robotics, computer hardware, and software. And simultaneously, post-World War prosperity increased the disposable incomes of many people and created demand for consumer products like telephones and household appliances, cameras, and audio equipment. Academia, government, and industry sponsored R&D pipelines to expand these concepts and to develop a way to fill consumer demand more rapidly and at lower cost. Academia asks the questions about what is possible and lays out the path for expanding our knowledge in science and technology. Government funding efforts reduce the invention risk by analyzing what technology is missing and what new inventions are needed to achieve the objectives proposed by the science community. And then industry searches and finds new and innovative applications for the new inventions, and then finds low-cost ways to deliver new products and services to as many people as possible. So since the 1990s, the pace of this cycle is accelerated by leveraging venture capital to fund new projects, using lean manufacturing and agile software development techniques to rapidly prototype and test new products, selling consumers continuously upgraded products, which generates a stable revenue stream that can be reinvested into further product development. That there's an unintended consequence of all of this. And that is to get the latest technology, consumers buy updated products every 1 to 3 years. And this generates a larger amount of discarded phones, computers, toasters, microwaves, you name it. There's probably a huge trash dump filled with these nifty new gadgets. And it's growing. There's an estimated 4.9 million metric tons of e-waste generated in 2018. So the core thing to understand is that continual upgrade and adoption of the latest technology is a feature of how this technology development stream works. And it was designed to drive a rapid scale up in technology. But the downside of this is large amounts of e-waste. So this is just a graph kind of showing how that the metric tons of e-waste increase year over year. And this is a cost that is not really taken into account in the model. E-waste creates hazards to the health and well-being of people living near and around electronic dumps. And there's the ongoing resource extraction and management of the waste stream that has a huge impact on the environment. I just want to credit T. Wang, who created the statistic display in this slide here. But it's predicted that there'll be over 5 million metric tons of e-waste globally. And the majority of it was generated around the world from these small electronic equipment. So the parallel to the space industry, the parallels are starting to really click now. Here's an example of an early Canadian space program. This is Alouette. And in 1962, Canada became the third country to launch a satellite into space with Alouette-1. This was a partnership with NASA providing the launch and the DRTE leading the development of the mission and satellite, with RCA and SPAR Aerospace developing key hardware technologies. And this was in many ways like our 1950s era phone, very well built. Lots of advanced planning and engineering intended to last 1 year, but operated for 10 years with a very, very successful science mission. And it was followed by Alouette 2, ISIS, and ISIS 2 that were launched quite rapidly after the initial launch in 1962. So the space industry has undergone a similar evolution as the consumer electronics market and what we saw with the telephone and mobile phone market. Today, the space industry is seeing a variety of satellite platforms, from commercially led flagship quality EO missions like RADARSAT-2 to mid-sized constellations funded by the government, RCM, and also very small microsatellite constellations that are marketed to the commercial industry, such as Rapid Eye, which was originally built for Blackbridge here in Canada and then sold to Planet, which operated the Rapid Eye satellites until just this year, where they were retired. The Rapid Eye satellites had an original mission lifetime of 7 years and operated very well for 10. So the space industry has undergone a similar evolution. In the 1960s and through the 2000s, we've developed a rich heritage of space mission design. In the 1990s and 2000s, we started using COTS components from the automotive and mobile device industries to reduce the cost and time to market for these satellites. And mobile mapping and search applications on these very telephones that we've been talking about creates a consumer demand for up-to-date Earth observation data. And so the industry funds the development of new space-enabled products. Venture capital funds the development of new space platforms. And small teams rapidly build, launch, and test these new satellites, which creates that stable revenue stream that allows for continuous upgrades in satellite capabilities. And that networking these satellites together can enable even more innovative satellite products and services. But similarly to the e-waste problem, we see a similar buildup of space debris, and particularly in low Earth orbit. And unfortunately, this rapid upgrade cycle is part of the system by design. You can't really get the latest and greatest computer without replacing your satellites on a relatively short time span. And that those technological advances bring real life benefits. They bring internet and mobile phone connectivity into remote areas of the world, like sub-Saharan Africa and Southeast Asia, which were not well served by landlines. Mapping and navigation applications that help everything from commercial shipping to in our personal lives, finding a way to the local pizza place. Emergency and disaster response. Canada leads the world in Arctic search and rescue operations that is enabled by space technology developed in Canada, land use, agricultural monitoring, and climate and environmental research. And so we really need to figure out solutions that can address the space debris problem, but we can't ignore the benefit that rapid technology scale-up have on the development of space technology, because that's setting ourselves up for failure. So we have to work out a system where we can have this rapid iteration, but without collecting a bunch of junk in orbit. So how do we keep the benefit of rapid iteration and technology advancement, but avoid the junk? And so this is where I would assert that we need to do more research into investigating what the consumer electronics industry has done. They've recognized the problem as well, and they've started several initiatives on developing a green supply chain, which makes better use of reclaiming precious minerals and recycling things so that they don't just collect in these huge dumps. And the space industry could perhaps learn quite a lot from that. Some other suggestions that are coming from the industry in general, a lot of times tech demos or classroom space projects will be launched into low Earth orbit, and they're only intended to operate for a year or two. And so if we launch these satellites into low Earth orbit, so orbits less than 300 kilometers or below, it turns out there's still enough atmosphere at that level that the drag on the satellites is quite a lot higher. And so you're not going to have that satellite hanging out for years and years and years. It will probably deorbit itself relatively rapidly within 2 or 3 years of it being launched. We could push for incorporating propulsion in all spacecraft operating in space. This helps us because we can avoid collisions in space by monitoring the satellite's positions and moving out of the way. It also means that when the satellite comes to end of mission life, it can be deorbited or moved into a graveyard orbit. For satellites that don't want to have the cost of propulsion, or for rocket bodies, and then it turns out a large amount of the debris in space are the abandoned third stages of rockets that deliver these satellites into orbit. We incorporate deorbit technology into these items, and there are a number of really interesting ideas out there. Ribbon technologies that increase the drag, nets, parachutes, tiny little thrusters that get put on these bodies. We can do that and get rid of things that are no longer serviceable and operating out of low Earth orbit. Develop onboard systems to detect and avoid collision threats in low Earth orbit. And so one of the issues you find is that when things crash into each other, they break up into tiny little bits and strew a huge debris field throughout low Earth orbit, which causes threats to operating satellites, as well as creating a huge debris cloud. And then, I would love to see more and more on-orbit service and upgrade and repair technologies for existing space platforms. So instead, I've heard it said space is one of the few places where you develop a vehicle, you give it a really large, huge gas tank, and then when the gas tank runs out of fuel, you abandon the vehicle. And so creating missions where you can go up and refuel and service and repair satellites so they can stay in service for longer, where their computer chip, their computer processors can be upgraded, their antennas can be upgraded, but you don't rebuild the entire satellite from scratch each and every time, would be another way to address the debris issue. And then maybe even developing and designing space missions that go out and salvage and reclaim debris. So instead of abandoning satellites in orbit, we do similar things as the consumer electronics industry is, which is instead of throwing your phone in the trash, when you upgrade, you trade it back in, and the company takes that device and disassembles it and takes out the precious metals in the computer chips and recycles the glass and the plastic, and they don't end up in the trash stream. They end up recycled into additional products. And so these are some of the ideas. I'm sure there are many others that we need to start thinking about so that we address the debris problem in low Earth and increasingly in mid-Earth and geostationary orbit, so that we avoid some of the issues we found here on Earth with the consumer electronics industry. And so that concludes my prepared remarks, but I am free for additional questions if the team would like to chat. You're on mute still, Ahmad.
Oh. Thanks, Ellen. Oh, thanks so much for that. I'm just going to see here. So if anybody has any questions at all, if you're able to do so, just go on the participant tab and just click the blue hand, and I'll start calling people out for to ask questions. So first up, we have Professor Cohen.
Hi, thanks for that talk. That was really interesting. So I guess I have a question thinking about like sustainable space stuff. What is the, like as a shot from the hip, how easy is it to estimate the carbon footprint of a space satellite? Like, is it fair, like just continuing with the analogy with the cell phones, is it fair to take the carbon footprint of say an iPhone and multiply it by the ratio of masses between like an iPhone and a satellite and say like order of magnitude, it's like, a half ton of super high tech widget, and therefore its carbon footprint is sort of comparable pound for pound to like an iPhone. Does that make sense?
That's a very interesting question. I don't think I've ever heard it put quite that way. I've heard discussions about the mass of objects in space, but the carbon footprint is a slightly different twist, and I haven't ever really thought about it in those terms. And I guess my first thought would be, it depends a little bit on the platform. I think if you were to compare it to one of Planet's doves, you're probably only talking a carbon footprint, since they literally use the types of cameras and processors that would go in a cell phone, and they're 10 by 10 by 30 centimeters. That's probably a lot less than say RCM with 3 satellites that are in the order of 700 kilograms each. I'm imagining the carbon footprint there is quite a bit higher, but I have not heard it discussed in those terms.
Do we have any other questions? Oh, Professor Smith. Sorry, Professor Smith, you're not on mute, but we can't hear you.
Can you hear me any better now?
Yeah.
Yes.
Great, okay. For some reason, Zoom had me on mute, a separate mute. So it's really interesting to think about the space debris, and I appreciate the talk about that. And I'm thinking about, or my question is about, what are the hazards besides loss of money? So if you launch a satellite and something hits it, of course you lose your satellite and all the investment there. Are there any hazards thinking beyond just cost? So, for example, if something came down, it could maybe land in a city center, probably they burn up. Have you thought about other hazards?
So the major hazard of space collisions, obviously the original collision will destroy the 2 objects that collided. But the bigger issue, and I didn't think to include it in this presentation, but when two satellites collide, and if you remember the Iridium Cosmos collision in the late 2000s, it created this huge, absolutely huge debris field. And so one of the things is, and I think Aaron has the plot, so maybe he can put that up, but a lot of it created these huge debris fields that created a huge amount of fast-moving debris that then could hit other satellites. And in fact, a scientist working at NASA, Dr. Kessler, had proposed a syndrome called Kessler Syndrome now, that basically says you create this situation where you create a cascade of collisions. So the debris from one collision goes on and strikes another satellite, which creates another debris field. And you can really have this, situation where you could make the ability to operate any satellite in certain altitudes completely impossible, because you've polluted the orbital plane with so many particles that it's just impossible to keep anything safe and operable in the environment.
Okay. And then of course that would have implications for defense or communications. So yeah,
Yes.
It's a huge increase in number, a factor of 2, it looks like. Okay, thank you.
Yeah, and so this plot here that Aaron has put up, I guess in around 2007, this is when you can see that part where the blue and the green lines go completely vertical. That's when the Iridium Cosmos collision happened. And you can see this huge cloud of debris that was created by those two satellites. Just really created just a whole nother level of hazard in that altitude that the two satellites operate.
If I could just comment very quickly, here's the
Yeah.
Iridium Cosmos of 2009 and the 2007. That's the Chinese ASAT test.
Ah, yes.
If I may ask a follow-up, I see, barring some big increase, there's usually some downward trend. Is are these pieces that are entering the atmosphere and coming down?
So for the most part, unless you're talking very low Earth orbit, there isn't generally enough atmosphere for things to deorbit naturally. And so unless you take some sort of active action, I believe the guidelines that currently are in place is that satellites need to deorbit naturally within 25 years of being launched. And many of the newer, but that's voluntary, many of the actors in space in the Western world do voluntarily follow these guidelines, but 25 years is a long time to be up there. And if you imagine a situation where you've got people like Elon Musk and Jeff Bezos launching thousands of satellites every year, you never get to a point where the natural attrition counterbalances the large scale up in more and more satellites being launched.
Okay, thanks.
Do we have any other questions? Yeah. Oh, Professor Lee.
Thanks for the really interesting talk. Maybe I just missed this, but could you tell us about the percentage of the orbiting bodies up there that are considered debris, as well as sort of like area or orbital coverage of those, like the coverage fraction?
So I believe Aaron just put a slide up on this.
I have that density
I would
plot
say
if you
it's
want.
like, yeah.
Sorry.
It's on the order of, yeah. Sorry.
Sorry, I didn't mean to interrupt. I have the density
That's okay.
altitude
Go
plot
ahead.
that I'll put up as soon as I can find it.
Okay. But one of the interesting things to know, just off the top of my head, I would say something on the order of only 10% of the objects up there are operating satellites. The overwhelming majority of this is debris, abandoned hardware. In particular, rocket bodies creates an overwhelming majority of the items up there in space right now. And so having that deorbit technology on things, once they're no longer operable or useful, would be a really big step in the right direction.
Yeah, that's a frightening number.
Yes. The issue also is right now, currently, the largest issue is in low Earth orbit and IS. So you can see, depending on your altitude, and you can see it at around 300, there are very few items there, and that is because the atmosphere does clean those orbital altitudes very efficiently. That means it's an unattractive place to launch a satellite if you want it to remain operable for anything more than 1 or 2 years. But you can see, especially around between 500 and 1,000 kilometers, it's mostly debris. The other thing to note, of course, is certain orbital altitudes are especially useful. There are altitudes where a satellite that may be an Earth observing satellite can have a repeating track. So their instrument can sweep along the same track path of location on the Earth. And they, 15 days later, when they come back, they'll sweep right over the exact same location on Earth. And so it's very easy to register images. Whereas other orbital altitudes, you kind of have this procession of your imagery across the globe. Things never quite line up. Mm-hmm. And you can, of course, address that in computer software after the fact, but it is a bit more work.
I have another question by Professor Cohen.
Is there, aside from the sort of space debris argument, will we ever reach a point where there'll be like a shortage of some of the rare earth elements or whatever goes into these spacecraft, that it would actually be economically viable to go and scoop up some of the space debris and collect it? Or maybe the deal is that it's like a carbon tax where you have to put a tax on space debris and you price it such that people are incentivized to clean up after themselves?
That's an excellent question. So when you talk about resource extraction here on Earth, it turns out mining, particularly precious, that mining steel and things like that, going to the moon and extracting iron from the surface, that's all extraordinarily expensive currently. And so it's not a cost-saving method. Even when you take into the account of launching and lifting that iron or the raw materials into space, it's much more cost-effective to get that on Earth and bring it up into orbit currently under the current number of satellite missions and all of that. I think where we start to see the tipping point is not so much with precious metals, but with water. So if you think about actually establishing, the Lunar Gateway and establishing a colony on the moon and having a human presence, that's going to take an extraordinary amount of water. And water is a very strained resource here on Earth. And so when it comes to mining resources or recovering resources directly in space, water is going to be the thing that is going to be the most cost effective and the most important thing to get first. Following that, at some point, with increases in technology, mining asteroids for the platinum group metals is the next, and it comes in far secondary in terms of a cost-saving measure. And so extracting it from Earth and launching it into space currently is much cheaper. So you would have to put in place some sort of incentive, whether it's taxes or not being able to get a license, or there have to be measures imposed by governments and international treaties to make that happen. beyond just a, oh, wow, this is a cool tech demo.
We have one question from Alexander in the chat. So Alexander's asking, from a space policy standpoint, does Canada have any programs or policies that ensure sustainability in space technologies? In your opinion, is this enough? And how does Canada compare to the global stage?
So I would say that Canada does have some policies in place that touch on these issues. So in order to get a license to launch, you do have to have a plan for what you're going to do when the satellite reaches end of life. And that plan usually follows international norms and guidelines, which is, you know, it has to deorbit within 25 years or you have to move it to a graveyard orbit. But enforcement is difficult. And I think the consensus is building, and this is something the Outer Space Institute spends a lot of time lobbying for and discussing and being a thought leader on, is we need to update this, right? The current guidelines were designed for the Apollo era space mission when, you know, a handful, you know, so former Soviet Union, the US, Canada, Europe, you know, a handful of actors were regularly launching into space, and they were these big programs with a lot of technology development, but a relatively small number of satellites. And now the floodgates are opening, and particularly in low Earth orbit, you're seeing, you know, anybody who has the funds, Bezos, Musk, Greg Weiler, you know, launching these mega constellations, and there aren't enough policies and programs to mitigate the impact. And getting them is difficult because it requires international treaties.
Any other questions?
I noticed Alexandra had a little bit of a follow-up on that, which was, how does Canada compare on the global stage? And I would say Canada is one of the leaders in trying to address this, and really has always taken this seriously and has tried to follow industry best practices. It's just a hard problem when you have to get all of the world's spacefaring nations and commercial industry all on the same page. It can be a bit tough.
Any other questions? So take a look here. Going once, going twice. All right. I guess we can all give Ellyne another round of applause, a Zoom round of applause.
Thank you.
Perfect. So thank you so much, Ellyne, again for coming today. Very enlightening talk. And we'll see everybody on January 13th for the next TEPS seminar. Okay. Take care. Have a good one.
Hi, everyone.